Hello, welcome to the EEE 300 overview presentation. This is the first of what will be 6 presentations in this project. We're going to go over a few key concepts from the course along with the case study. I'm Hannah, and in my group is Kaylee, Anna-Marie, and Nate, and you will hear us talk throughout the series of presentations. This class focused on modeling systems. Being able to model systems is key to environmental engineering. For example, you could have pollution entering a stream as shown in the illustration on this slide. As an engineer, you might want to model the concentration over time or the concentration over distance to see how far it'll travel. Really anything about the pollution characteristics that could be relevant to the problem you're trying to solve. You could also measure water quality, such as the oxygen in the water. As you can see in this picture, there's a lot less oxygen closer to the pollution and a lot more as you get further away. Being able to measure water quality is important for things like fish who need oxygen to breathe. Being able to put these two together, you can look at the relationship between the concentration over distance and the oxygen concentration over distance, and you can see how the pollution could potentially be affecting the oxygen in the fish. In order to successfully model systems, you're going to need some background knowledge. This includes engineering, chemistry, math, and computer science. Engineering is important because it provides you with the necessary problem-solving skills to tackle any systems that you could be modeling. Chemistry is important because, as mentioned in the previous example, you need to know how certain things in the environment interact with each other, and that's all related to chemistry. You also need to know math. There's a lot of differential equations that deal with rates of, say, the pollution decay in the water, in which case you need to understand how to solve these differential equations in order to create accurate system models. And you also need to know computer science. That is because computers make modeling so much easier. Instead of doing an iterative process by hand, which could take hours, a computer can do it in what seems like mere seconds. This makes the process of modeling go much faster and also removes a lot of potential for mistakes, such as doing 2 + 2 = 5. For the sake of this project, we're going to be using Matlab, which is what we use throughout this course. The case study we are going to focus on is chlorine decay in water. You can think of this similar to the illustration shown earlier where the pollution was entering a stream and became less as it went down the stream. The same thing happens with chlorine in water systems. This study will focus on chlorine decay in water. Chlorine has many uses, one of which is to treat drinking water. Its main purpose is to act as a disinfectant, meaning it neutralizes bacteria that could be harmful to human health. It also has been shown to improve the taste of water and also reduce the odor. One of the reasons chlorine is used as opposed to other treatment methods is that it's relatively cheap to apply on a large scale. However, chlorine can be harmful if it's found in large quantities in the water. That's why decay is important to safety. The chlorine needs to be strong enough to kill microorganisms along the way, but weak enough that it won't harm the end users, such as you getting a glass of water from your tap. Models can be used to predict decay following kinetic reactions. One of the sources we used for this study was reactions of chlorine with inorganic and organic compounds during water treatment, Kinetics and Mechanisms, a Critical Review by DeBord and von Guten. They look at how chlorine interacts with inorganic and organic materials and how it decays throughout the system. As I mentioned previously, this project will go over a few concepts discussed in class. The first concept is reaction kinetics. Reaction kinetics are the rate of chemical reactions that happen at the molecular level. Relating this back to the case study of chlorine decay in water, the chlorine decays because it is reacting with various things in its environment. This can be modeled by reaction kinetics. Oftentimes, reaction kinetics will use a rate constant of lowercase k. It is important to note that multiple k values can exist for a process. For example, if you start with compound A and end with compound C, there could be an intermediate step. So you could go from A to B using K1, and then B to C using K2 if they happen at different rates. Or it can be a simpler reaction where it just goes from A to B, and B is the final product, so you'd only have one rate constant. Reaction kinetics are very important to many processes, not just to the case study I mentioned earlier, but also in industry. For example, if a company is trying to make a process more efficient, they can use a catalyst which would adjust the rate constant and could cause the reaction to go faster and therefore take less time to reach the end product. It can also be used to model pollution decay in air or water. Say, for example, there's a chemical plant that releases some kind of pollutant into the atmosphere. Scientists and engineers can do their best to model how this pollution will spread and how it will interact with its surroundings and become either neutralized or more toxic over time. Reaction kinetics can also be used to model cycles, such as the carbon cycle, nitrogen cycle, and ozone cycle. In essence, anything that reacts with its surroundings in a set way can be modeled by reaction kinetics. The other concept we'll be going over in this presentation is using Matlab to solve ODE functions. Matlab makes solving ODE functions much easier. As I explained earlier, Matlab can solve these very quickly as opposed to humans having to go through a multi-step process with sometimes very complicated calculations in order to achieve the same answer. We will focus on 3 ways to solve ODE functions in Matlab. The first will be the symbolic toolbox, the next will be Euler's method, and the last will be ODE 45. Another cool thing about using Matlab to solve these functions is you can get Matlab to plot the results. Plotting the results gives a more visual representation of what we're trying to solve, which can be helpful to understanding the material. For example, knowing the equation for how chlorine decays in water may be good to know, but being able to see how it's decaying relative to its distance traveled or relative to the time it's been sitting in the water can help provide a better understanding of how the chlorine is changing and when it would be safe to consume that water. Every video will end in a quiz. The quiz will be through Google Forms. Please click on the link, which will also be provided outside of the video, and solve the quiz. They should be multiple choice or true-false questions covered throughout each presentation. There will be one quiz for each presentation. At the end of the quiz, you can submit it. When you submit it, you'll be given the option to view your graded results. Your graded results will show you how many you got right and how many you got wrong. It will also show the correct answer. If you have any questions about the quizzes, please feel free to reach out to our group.